just joined us for this session. My name is Mushtaba Walipur, and I'm a PhD student of computer science at the University of Waterloo. I'm the session chair of this for this session. Before I just forget things, the organizer asked me that if you had any kind of problem, please refer to their website and just send them email. So if you have any kind of question, please feel free to do that. You can find the contact information on their website. Today, actually, the title of this session is structure inductive biases for generalization in robot learning. We proudly have Animesh Garg. He's an assistant professor of computer science at the University of Toronto and a faculty member at the Vector Institute. He directs the U of T People, AI and Robotics group. He's also a senior research scientist at NVIDIA. He earned his master in computer science and PhD in operation research from UC Berkeley. He worked with Ken Goldberg at Berkeley AI Research. He was later a postdoc at the Stanford AI Lab with Fei-Fei Li and Silvio Savarese. His current research focuses on machine learning algorithm for perception and contour in robotics. Please welcome Animesh Garg. We have him as a very live session. So if you just had a kind of question, maybe if he just feel that he can answer the question, he's absolutely free to do that. Yeah. Thank you so much, Animesh. Hi.
Thanks a lot, Mushtaba, for such a nice introduction. And thank you for all of the organizers for inviting me and actually putting together such a great program. Hopefully you guys have had a wonderful day and actually a week worth of very good lectures. At least I can say that for myself. So what I'm going to do is start the screen share.
Yeah, absolutely.
And hopefully this would be wonderful.
Yeah, perfect.
And yes, I think you should be able to see this now.
Yes, I can confirm that we can see it. Yeah.
Okay. Wonderful. So what we're going to do today is I'm going to talk about mainly a variety of sort of hierarchy of problems, particularly in decision making, with relevance and examples throughout robot manipulation. And the way I've structured this is I've tried to make it as descriptive as possible. At the same time, I would love for people to ask questions. Mushtaba, could you also monitor chat with that? Because I don't get to actually see the chat while I'm presenting in this mode, as you can see. So feel free to interrupt me if there are any questions, and I'll be happy to answer them as we go along. And of course, we can keep time at the end for any detailed questions as well. Okay, so let's get started without further sort of ado. I have been working on robot manipulation for about 8 to 10 years now, and I think I'm really motivated by this idea of what you would call out-of-the-box autonomy that has been promised to us by science fiction cartoons, where we have a system that is very sort of efficient and just works. And I think something like that has sort of driven the technical question of what sort of algorithmic methods can enable such efficient robot learning, particularly in manipulation. And the real aim here is to build autonomous systems that can operate in open world and challenging environments. Now, if we just think of this example, one particular robot might need to do a variety of things. Just a home robot may need to do vacuuming, sweeping, cooking, laundry. And this is just some of these small examples. And not only that, you would want these systems or this robot to actually work what you would call in a diversity of seats. So for example, if it needs to use the vacuum, it needs to be able to use vacuum in different cases, maybe slightly different variations of vacuums, and so on. And also solve similar problems, perhaps with more complexity. So if you teach a robot to clean a wall, then perhaps it should be able to clean a wall that was slightly more sort of dirtier, or a sink that is overflowing, or a laundry basket that is sort of out of hand in that sense. So it really needs to work in a variety of settings, in a more general purpose sense, very much outside the lab. So really, this challenge drives the vision that what we are really after is trying to build robot companions that are intelligent and help us enrich and augment humans in both cognitive and physical sense. So we are trying to solve problems with these systems that are often maybe tedious. They require cognitive effort from humans, and at the same time physical effort from the humans. But at the same time, we are not saying that we want human replacements, but really these machines will act as companions and tools going forward. Now, one would say that our efforts to build a robot in the kitchen are basically as old as our understanding and maybe interest in the term AI. So in fact, the term AI was done in 1956. And soon after, about 10 years after, we had these robot videos trying to make breakfast. So this is a video of the first industrial robot called Unimate in 1968. Of course, this video is completely structured or staged. But the idea is that humans were fascinated by having algorithmic agents in real world to help us. And in this case, the lady does her nails while the robot makes breakfast and serves it off. Now, one could argue that the dream has really not changed. So since 1968, this is a video from earlier in 2020, from the CES, Consumer Electronics Show in January, where this is a concept video by Sony trying to build a robotic kitchen system. And really, if you think about this, what we're trying to say over the last 50 years is that we need a system that is as generic as one of these things shown and can achieve the kind of tasks with the variety of tasks that we achieve in an everyday kitchen. And of course, remember, these are not industrial robots. They need to work in my kitchen, your kitchen, perhaps your mom's kitchen. So they need to be generalizable. But unfortunately, when we look at realistic robots in the real world, it turns out building systems like this is, well, really hard. And one would argue that even though we have built very smart, physically capable robots that can handle boxes, perhaps operate under teleoperation, the difference between what we have always sort of achieved and what we have wanted is this idea that we do not know how to generalize to unstructured scenarios in open world environment. And I've given you examples only in the kitchen, but there's nothing particularly special about the kitchen. The same sort of lack of generalization appears in manufacturing. It appears in retail. For example, let's say a retail store where you're trying to get food, or maybe personal robots and service robots, and also in healthcare and surgical robots. So then what I argue is a solution to such a problem is going to appear by building learning algorithms that have structured inductive biases and priors. And I'll explain what I mean by that as I go along. But the main idea really is that this process will involve two stages. One stage of the task is a mechanism to specify the task. Let's say demonstration. It can be teleoperation, videos, or language. And we need algorithms which can infer and understand the task from this set of demonstrations or specification and learn a policy in this particular space. Particularly, it can learn to do the task in the same or a very similar environment. And then we need a mechanism or algorithmic generalization to achieve this task with variations in novel environments. In this case, I basically give an example of a chair where you learn to build one chair, but then you can build new IKEA chairs without example. That said, imitation by itself is actually not trivial. So one could argue that, let's say, imitation is just the idea of copying, and we want something that we want to do from scratch. But I argue imitation requires a lot of cognitive detail. So let's take a very simple example of maybe gathering or raking leaves in your garden. So let's say the task specification is done by an adult. A small child looking at an adult might only copy the actual motion of the broom. So they may wave the broom around, maybe looking at them, but really that doesn't necessarily achieve the task. But as the child grows up and their cognitive ability grows up, they realize perhaps they need to also achieve the task. So they start to do the same task with the same tool. And as they grow up even more, their understanding of the task and the perception improves to a point where they're able to achieve the task objective in a manner that is different from the task specification, which is what one could argue is the mark of intelligence. So what I'm going to talk about today is basically follow a very similar hierarchy of problems. And the way I think about these four problems, control, planning, perception, and the use of data, is to build any sort of practical robotic systems, we have to think about these things in a manner where we are thinking about problems holistically. Particularly, we are trying to unify control, planning, perception through learning, and we are trying to understand how each other they affect each other in a manner that that can be leveraged in designing algorithms. And again, as I said, the kind of applications for these things are very broad, starting from home applications to manufacturing, retail applications, and healthcare and surgery. So today, what I'm going to talk about is give you a few examples across this hierarchy of problems, starting with control, where we talk about Visuo-Motor skills. So we are talking about low-level control skills. Then we go on to talk about planning, which would be slightly more complicated or multi-stage tasks. Then we will talk about the use of perception to do one-shot imitation learning. And then finally, we'll talk about how data affects all of these stages and how can we leverage large-scale data collection in robotics that can power the next generation of learning algorithms in robotics. Okay, let's get started. So let's get started with controls first. So if you remember the first slide that I showed you, the robot was doing a variety of skills from vacuuming, sweeping, cooking, cleaning, and so on. And what we are after is some sort of algorithmic framework that will allow us to learn some diversity of skills. So just to recap, we want an algorithmic system where we do not need to tune the algorithm for vacuuming, sweeping, cooking, cleaning, and so on. And ideally, we want to be able to do this with visual input. Only then we will be able to create a system that would be able to do this without requiring task-specific perception. Okay. So let's consider one of these tasks. Maybe it's cleaning. So cleaning is something where it is an abstraction of a task that appears almost everywhere, many times during the day. Of course, a robot may not be wiping a radio. Not many people have both robots and radios in their houses at the same time. But nonetheless, wiping a kitchen top or wiping a whiteboard is very commonplace. However, the thing of interest is we need to be able to design algorithms which are smart enough to understand perhaps they need to push harder if the stain is harder, or perhaps to be gentle when they're cleaning glass. Otherwise, they might even break the glass itself. So they need to be able to generalize to slightly harder stains, new surfaces. Maybe the shape of the surface is not known a priori, so on and so forth. Now let's think about how we can solve this problem in the current paradigm. The current paradigm can be something where you have a reinforcement learning kind of setup. A reinforcement learning setup has a mechanism where you have some image input. Image is fed to a policy. The policy can be a neural network structure, and the policy outputs some amount of control. In this case, the robot control can be done in the form of joint torques. Now, this model, particularly in the last 5 years, has yielded very exciting results. This is completely model-free in the sense that I do not need to model the environment or its dynamics explicitly. I can use state as an image, which is very important because I do not need to explicitly build, let's say, object classifiers, object trackers, and so on and so forth. And this works out of the box in that sense. But at the same time, there are a few problems. First, training such a policy, even with a lot of compute, is actually sample inefficient. Two, whenever we are trying to do this, when I'm doing this image to torque, there's a part of the system which has to learn the robot model implicitly. It has to learn how to move the joint so that what sort of torques result in where the arm is. That sort of knowledge is being learned and relearned over and over again. And finally, there's a problem with robustness. If training is not equal to testing or approximately equal to testing in case of reinforcement learning, generalization is very hard. So if you train and you test on a slightly different environment, policy is very likely to fail. Now, on the contrary, a more conventional robotics approach to doing something like this would be to use what you would call model-based control. So model-based control basically implies that you have a mechanism of what you would call reference generation. So you tell what the task is specifically. This reference generation is essentially a desired state. You use the robot model to compute an action for this desired state, and then you go from there to compute sort of what the next state in the environment would be, and you use an environment model at this point to move to the next stages in the task. But the problem here is, or first of all, actually, the good things about this model is the fact that you can use the environment model. It allows you to have compliant control. Compliant control is basically saying that the robot learns to be soft, so it will not shatter glass or maybe result in hard collisions or hurt people. But at the same time, the problem here is that you still need a task model. So to clean up a table, one has to explicitly write that the first step is going to the table, then the second step is wiping the table, and perhaps so on and so forth. And if something goes wrong, then I have to write error checkings and be able to handle errors. Otherwise, the system becomes very prone to error and will fail very often. And secondly, whenever I'm using some mechanism of state generation or a model, usually the model is in explicit states. So what I mean by explicit state is, let's say I can write these equations maybe if I know the pose of the object. And to know the pose of the object, I have to write a pose detector. And then a pose detector will often be task specific. So I have to create a task dependent state, and I have to do explicit state estimation. This is actually limiting because this limits where I can apply this algorithm to generally. So now what we're basically thinking about is, can we have a mechanism where we have best of both worlds? So can we have an algorithmic approach which will allow us to get, let's say, the best parts of having an RL agent, and at the same time, the sample efficiency of model-based control? So if we think about reinforcement learning, what is really happening? One of the things that is happening is you can have an observation, let's say an image. The image is fed to a policy, but instead of using a policy directly as robot controller, we use or we think of this as a reference generator. in the model-based setup. And now we pass this reference as a parameter to a robot model. So remember, what we are doing here is we are basically saying that there is a lot of the environment that we do not know and do not want to model. So I cannot model what, for example, the shape of this cup is, or how the water will behave in this cup. So I will let the policy handle that. But at the same time, I do know what my robot is doing, and repeatedly, I don't need to learn that model. So I can abstract the environment into pi and the robot into f. It is slightly more nuanced here. Uh, the choice of action space, the action space is the output of function pi, is very important here. So I make the choice of action space to be such that it is a reference for the robot. So instead of operating in tasks in joint space, which is basically asking the policy to control all of the joints, so let's say the elbow and the shoulder, it is only controlling the point which actually interacts with the environment, which is the end effector. One, and then the action space of this end effector is position and velocity, and what you would call impedance gains. So impedance gains are basically parameters which control how stiffly the hand will move in what direction. This is what is used for different stages of the task. For example, when you're going down towards a table, you are free to move in all directions. When you are now wiping the table, you have high gains in vertical direction and low gains in along the surface, which basically means that you want to maintain contact while you are wiping. Usually, this gain scheduling is done manually with the knowledge of task. But by doing this as an action space, we allow the policy to learn how to do this gain scheduling. And then once we have this as an action space, we can directly pass this into the robot and ask the robot to basically convert this action space of end effector into task spaces. The good thing about doing something like this is we have no environment model. So we are able to do image to control learning. The state is image indeed. At the same time, we keep everything that was good about robotics by knowing the model. So we still get compliant control, we get very efficient control, and the system is very transferable, as I'll talk about. So an example of this idea can be thought of here, where you have the surface wiping example. The image in the inset is what the policy sees. The outer image is only for illustration. There is a reward model, which is basically simple, that you have to minimize the number of dirty tiles on the table. You have to maintain contact with the table, and you don't want to push too hard. That might break the robot. And what we're going to see here is we compare a variety of different action spaces. Just to give you a sense, what is action space? The action space is the output space of pi. So we have designed the controller for different choices of action spaces that are used and compared them. And what you really need to only see is among different variations, whether you go from joint torques, which are directly images to joint torques, versus images to a particular kind of structured representation of action space, there is a lot of difference in learning and learning efficiency. In fact, after 1 million time steps of an RL algorithm, we see that the difference can be actually between failure and success. Then, as I said, because we have separated how the robot and the policy are interacting, we can really only change the outer loop, which is F, and directly go from simulation to a real world system without retraining or doing any sort of sim to real business. And in this case, as you might observe, that going from simulation to reality does not require any transfer, but yet we achieve a very high success. Of course, this can be improved, but the whole point of this experiment is to show that with using some particular structure, we get a lot of efficiency. Moving forward, So far, I talked about an algorithm which is doing reinforcement learning with a particular kind of structure of action space. And what I talked about is by choosing the right action space, which is basically the structure in the problem, we can get a lot of efficiency in both learning and also make it much more practical by being able to transfer to a real world. Moving on, let's look at yet another problem in reinforcement learning. So as we said, the promise of deep reinforcement learning is this idea of closed loop control with images. But of course, it requires a lot of real training. And this is something that not everybody may have access to. So not everybody may have access to, let's say, a battery of robot arms that can run for months to give us training data. What instead we might like is a mechanism where we can code up very quickly some parts of the solution as a programmer, and then the system can figure this out on the fly. In fact, people have shown very recently is that even simple heuristics that programmers or domain experts can code up can actually beat reinforcement learning with a lot of training. So now the question was, again, can we use these expert intuition, an expert being the programmer or myself or a robotics engineer, to help reinforcement learning algorithm learn faster? So the reason why we would need such a heuristic is basically that exploration in environments is very slow. And this example is a very simple sort of example to give here is, even though the obvious thing to do in this case is to actually just go to the door handle. And despite that, the robot spends a lot of the time figuring out how to sort of poke around and get to the handle. So the question really we were saying is, or we were exploring is, can human intuition guide exploration and make this system go faster? So let's consider this simple task. The task is to move a block from particular position to a goal position. The block can be farther away from the robot, but there is a tool that is given to a robot, and the system can actually use the tool to hook and pull the object. So one thing we can think about is we can think about creating very simple policies that we can code up quickly enough, where maybe reach the tool or push or pull the tool or put the robot in these positions. But again, and we are basically looking for an agent that is guided by these teachers to complete this task. And the goal here is that we want faster agent training, and at test time, we don't want to be able to, or the need to use any of these teachers. So we want to train an RL agent that will achieve the task without the need of any of these heuristics. But it is non-trivial to think about how to use these heuristics. One problem can be that maybe the set of heuristics that we have provided is actually incomplete. So maybe I talked about how to reach the tool, but I did not actually talk about how to sequence these heuristics. Maybe there was a gap in my knowledge. So I told the system that there is how to get to the tool is included, but nothing else is included. So although it is partial information and it is useful, it is not complete, or it is not enough information that will let me train a full policy just by looking at heuristics. At the same time, I might have these heuristics which are just small parts of the task. They don't do the whole task, maybe grasping or maybe pulling. If I apply both heuristics in the same state, they might even be contradictory to the overall objective. So I need to come up with an algorithm which can handle using these heuristics or as experts only when needed, and then filling the gap with reinforcement learning as and when required. So from an algorithmic perspective, what does this mean? This means something like this. You start with an environment given a state, and you want to train an actor policy that will operate in this state. But at the same time, you also have a few teachers that can help you. Teachers are basically these heuristic policies that may have access to, let's say, specialized information that the agent does not have. Now, each of them can output a different action for a given state. What we need is to train a model that can evaluate which of these actions is actually the best thing to do right now. So at this point, what we do is we train a two-stage policy. At a high level, there's a high-level critic, which is basically choosing which of these actions is the right thing to do. Given a particular action, I will pick that particular policy. So let's say, in this case, teacher one is chosen. So teacher one is what I will choose. I will play out that actual action in the environment. If it turns out that the action was chosen by a teacher, not by the policy, then this action, state action and state pair goes into a learning buffer. Because I'm doing what I call off-policy reinforcement learning, what I can do here is I can train the policy pi even when the action came from a different teacher. So what is happening here is, in the beginning of the training, my policy knows nothing. So it is almost always outputting random actions. So the critic learns to pick other teachers. But as time goes by, the actor policy, the pi, learns from the actions of teachers to play the best teacher whenever needed. And when there is no information from the teachers, as in all teachers are bad for a particular given state, then we are running essentially reinforcement learning at that point. So we are being basically able to use the right teacher, and whenever there is no teacher available, we can use reinforcement learning. So now for experiments, so the same task, we have 4 teachers. We have grab hook, position hook, pull, and push. Remember, there is no sort of information of how to chain them or if they are chainable at all. So we are going to compare this with 3 different methods. First is Bayesian DDPG with AC teach. That is our method. DQN is a simpler method of choosing high-level, low-level actions and no teachers. So of course, what we see is not providing any teachers is very slow. At the same time, providing a full AC teach method is much faster than a vanilla RL method like DDPG. More interestingly, so if you have a single teacher, of course, this improves learning. If you are given multiple teachers, then AC teach is the only algorithm that works. DDPG stops working because you need a mechanism at a high level to pick the right teacher. In fact, AC teach is able to learn the method when behavior is not in the teacher set. So as I said, that not all teachers, the set is not complete. So what I basically talked about in the last 10 to 15 minutes is actually this idea that first, when you are doing controls, picking the right action space is very important and can help you achieve better generalization and better transfer. And when the choice of, or the mechanism to be able to provide some weak supervision to reinforcement learning methods can provide a lot of structure that enables efficiency and at the same time generalization. So I want to take a pause here for a second and ask if there are any questions so far.
There might be a question.
If there are no questions, we will proceed. Mustafa?
It seems that there is a question, but in the meanwhile that she just asked her question, I can actually ask a couple of questions. So, you know, for the training and testing that you just mentioned in the in the first slides, do you mean that they had to have different kind of distribution, or no, just this, even for the same distribution they are going to have the problem for generalization?
So often distribution means maybe different things. Maybe let's say distribution can mean the environment distribution. So maybe the task is to push an object, but the mass of the object changes. So that is one kind of variation. Another kind of variation can be let's say the robot itself is changing. Maybe let's say the robot's motors are heating up and the dynamics of the robots are changing. Another way you can think of where the change can happen is maybe the lighting or the time of day is changing. So all of these variations can result in a variation of the environmental setup, which can result in failure of the policy.
Okay, I see. Perfect. As another question, because your talk is mostly about the inductive bias. Usually in AI, for example, very recently from StyleGAN, they just actually the whole point was that somehow incorporate some inductive bias in the architecture design of the neural network. So do you think that we can also use this kind of inductive bias, for reinforcement learning problems?
Yes, I will talk about this going forward. The
Perfect.
talk is far from over right now. We have only
Yeah, sure.
talked about one section, so there are 3 more
Okay,
sections
nice.
to go. Okay,
Okay, nice.
so
Yeah.
in the interest of
So
time,
maybe
short
if we
answer
just
is
ask.
yes. The short answer is yes. What I've
Oh,
just showed is that providing a particular kind of structure to the input and output was useful. Providing some sort of weak supervision was useful. We will also talk about how we can actually change the structure of the model itself as well.
okay,
Any
nice.
further questions, Mushtaba?
Actually, one of the participant, Mobini, just asked the question. I'm not sure if I can publish it now. Let me see if I can do that actually. Yeah, it seems that
I
I can.
I don't see the question, but can you just repeat the question for me?
Yeah, yeah, here. Mobina just asked that when we are taking talking maybe about the teachers, are we referring to human experts or are they expert computer programs?
So when we're talking about teachers, teachers can be anything that is either a computer program or humans, but it's easier to think of computer programs. Think of it like this. If you are given a task of controlling this robot, maybe you can very quickly code up parts of the task. Maybe think about autonomous driving. It's easy to maybe code up how to do left turns and maybe lane changes independent of the big picture driving policy. The big picture driving policy is very hard to code up, but small parts of it are easy to code up. So think of these small parts as the teachers.
Okay, nice. As the next question, Aryan Sultani just asked that in many AI tasks such as NLP, we have the problem of incorporating common sense into the model. In a robotic task, it can be if you push a glass table too hard, it will break. Recent language models show good appreciation of this. Do you think this common sense knowledge can also be shared with the robotic context?
So I would say, in very briefly, it's hard to label something like that. The grounding of what is breaking is hard unless you have seen some mechanism of grounding. And when I say grounding in the sense, unless you understand the concept of shattering glass, it would be very hard to do this. Now, at the same time, uh, in reinforcement learning literature, I don't want to shatter glass 10,000 times to understand the concept. One example or a few examples should be enough. Uh, so I think what we are working towards across the community, not just me, is to figure out algorithms which can handle this in a few short cents rather than needing to have many examples. But at the same time, having zero examples will be very hard. It's like saying that I give you an object that you have never seen before. Uh, I don't know if you do not know what this is, and I ask you to sort of figure out. Sometimes it can be tricky. You need to have some mechanism of a prior to do this.
Okay, nice.
Okay.
Aliza Jamal Mardi just asked that can you use a neural network to help the agent to learn faster as an imitation learning? Because it's, I'm not sure.
That's what I will talk
Yeah.
about.
Okay, nice. Yeah, exactly.
Cool. Okay, so let's try to sort of like postpone some of these questions to the next
Sure.
stage, and
Yeah,
hopefully some of
perfect.
these questions will be answered as we go along. Okay,
Yeah, perfect. Yeah, nice.
Wonderful. So far, what I talked about is basically these independent skills. I talked about this sort of wiping task. I talked about maybe pushing and opening kind of thing. But often the real world may require the use of tools. The real world may require some sort of sequential tasks, right? So maybe figure out where to grasp the hammer and then how to use the hammer. So that is what we started looking at. It is a very, very sort of fundamental problem in study of manipulation. If I give you an object, the object identity is not known a priori. How will you use the tool for different tasks? So let's say one of the tasks is sweeping. So sweeping is you are given an object and you have to push the water bottle into the cup. The robot cannot touch the water bottle itself. It has to do it through an object. And the other task is hammering. And I don't need to explain what hammering is. Now, you are given an unknown object. Of course, in this case, you are given a hammer, but well, the system doesn't know what a hammer is. The system only sees maybe the 3D depth image of an arbitrary object. Now, the question is, how do we do this task? One way to think about this is maybe let's optimize for grasping first. So maybe I have a system which will grasp the object in a manner that is completely optimal. But I can argue that if you optimize for grasping, then you are not really optimizing for what the task is. Nobody grasps the hammer near the head to grasp it. They actually grab it far from the head to be able to use it as a hammer. So perhaps the grasp that you use for achieving a task is dependent on the task. But right now, the systems that we use for manipulation are optimizing these problems of grasping and task success separately. That's not an ideal thing to do. So what is the problem? The problem is that we are given some sort of depth image and some specification of the task. Now, the output of the policy in this case needs to be where to grasp the object. So some sort of point, some theta in the world coordinate frame. And then we still need a policy that the system needs to use the object with a particular grasp to achieve the task. Now, the search space in this case is actually very large, and it can be very hard to come up with a policy that will do both of these successful grasping and policy learning together. So the interesting thing here is to understand that we can factorize this problem. We can think of this problem of learning policy and grasping as a mechanism where we need to think about the chance of task success given a particular observation and a grasp G. Directly doing this can be very tricky, but realizing the causal direction of this setup is very important. So every time the task succeeds, you are fairly certain that the grasp succeeded. So in the sense that if you are able to achieve successful hammering, you must be able to grasp the hammer to begin. But the other way around is actually not true. The grasp success does not imply task success. You may be able to achieve a very good grasp, but it may be actually very bad for the task. Using this knowledge, we can use the factorized version of my score function in the right model. And then I can have a model which is doing grasp success and then task conditioned grasp success. Using this framework of factorization, I can now train the model jointly, where there are three things that I'm training for. I'm training a grasping model, I'm training a task-oriented grasping model, and then a policy. So the grasping model is trained with a standard loss function of being able to predict a particular grasp and the value of or the probability of success. Then you want to weight this grasping model given a particular task. Will this grasp be a good idea if we need to do the task at hand? And finally, given a grasp, can I come up with a policy? As you might imagine, we want to train this for a very large set of object shapes. So what we do is, instead of using real shapes, we generate arbitrary diverse hammers that are procedurally generated and train the whole system in simulation, about 1.5 million episodes. So now at test time, what we are given with the trained model is you have an arbitrary object, a depth image of an object to be very specific. Given a depth image, random grasps are sampled on the object. Given these grasps, we can go from grasp-oriented ranking of these grasps. So all of these graphs had high enough score that all of them will succeed independently. But if we think about the task, the ranking can enable us to pick a graph that is more suited for current task. Perhaps the hammer we want to grab at the blue region. If we were doing a different task, let's say sweeping, we might grab it at the head, so on and so forth. And then, given this, we want to learn a manipulation policy. In this case, what point to go to, how hard to hit the peg. And given the success of the manipulation policy, which is going to be the only reward. So there is no intermediate reward of succeeding in grasping and so on and so forth. It's just the task execution that is providing the reward. Now, by doing so, we again are able to train very general purpose policies that work with arbitrary objects that are maybe hammers, may not be hammers. And we see that we can achieve both hammering and sweeping tasks simultaneously. And what we see is comparing with baselines. So there is an anti-modal baseline, which is basically saying that you have a very simple heuristic of grasping, which is basically just grasp 2 points that are opposite, and then optimize for object success. So you're not optimizing for grasp success, but you're only optimizing for manipulation policy, and the task obviously fails because the object keeps dropping out. On the other hand, you can do this two-stage pipeline where I optimize for grasp success. So I come up with the optimal way of getting the object, and then I move on to optimal way of achieving the task. And it achieves about 30% success rate in hammering and sweeping. And what we see is we can double the performance if we jointly solve this thing. What we are basically saying is that our model jointly optimizes for grasping and task, not just grasping. And that way we can get much better performance of the system. One interesting thing to note here is because we use depth images, we can train the system purely on simulation and then go to real world without any fine tuning. And in this case, none of these objects that are in evaluation were in the training set. And again, we see a similar performance gain in real world environments as well. So now what I talked about is the use of sequential sort of, skills and by structuring the policy learning process in a manner that is multi-stage, yet using the right factorization enables us to do a very complex process of tool use into something that we can actually practically learn. Now, going forward, tool use is not just limited to simple one-step process. Tool use may actually require multi-stage reasoning. In this case, the task was very simple. The task is basically maybe move that green peg to closer to you, but there is this soup can that is an obstacle. And you need to realize that because the green peg can roll, you need to have an object that will support it. Otherwise, the green peg may just roll off the table. And you want to be able to do this sort of reasoning for multiple objects with different shapes. Maybe the object, the tool object that you're using itself is something that is not known. So how do you do this kind of reason? So this question we were basically thinking about led us to this problem. Can we learn multi-step reasoning? So hammering was just one step, but multi-step reasoning under physical and semantic constraints. So another way of thinking about this problem is in this sort of simple pushing domain, you have a particular object. The object needs to go to a goal position, but we have certain constraints. In this case, the constraint can be that the object needs to always be in a particular region, let's say in the path. It can never go in the restricted region. Then we can come up with a solution for this problem that will bring the object to the goal. Now, what if there are actual obstacles in the environment? And these are arbitrary objects of unknown type. Now, the original solution of pushing the Coke can will not work. Here we have to actually do discrete decision making. I have to first figure out that there is an obstacle in the environment. I need to push the obstacle out. and then I can push the Coke can along the path. So here, not only I'm making a continuous decision of what object to push and how I make continuous decision of how to push the Coke can, but also a discrete decision of at what point which object to push. So I'm basically doing decision making at a high level, doing discrete decisions which object to push, and doing continuous decisions how to actually push the object. So now something like this can be done with maybe learning the dynamics of the model or dynamics of the system. And I can train the model by choosing some sort of action sequence given this model. And this idea of learning models has actually been very successful of late in both reinforcement learning and robot learning in general. But one thing that we noticed is all of these cases, the model that is being learned, even if it is in the image spaces, is actually very, very short horizon. So basically what ends up happening is if I want to do long-term prediction, which requires me to take discrete decision making, then the amount of data required to learn such complicated tasks where I am making both discrete and continuous decisions simultaneously can actually grow very quickly. So then the suggested approach that we have is, let's learn a planner based on a model that is hierarchical. That's one. And two, the model is learning this dynamics in latent space. So we are basically leveraging hierarchical abstraction in the action space without having explicit hierarchical supervision. So when I say hierarchical supervision, I do not know what is the right high-level actions, but I only know low-level actions from my data. But at the same time, I want my model to discover such hierarchy implicitly. So what does this mean? This means that I have, let's say, a set of sub-goals that my effect code or high-level code can operate. So this is equivalent to saying that you are trying to go to the airport. So you think about how to get to the airport directly, but you don't think about every steps along the way to get to the airport. You basically think about getting the airport in high-level steps. Maybe you need to get to the train station, then take the train to a particular station, and then take the bus. Given an effect code, you can generate motion code. Once you know the next step right now is to get to the train station, you can actually figure out a low-level plan how to get to the train station in the big picture idea of getting to the airport. So here we are learning a metadynamics model, which is basically learning this high-level plan. Given a metadynamics model, I can learn an action generator, which is basically thinking about what I need to do right now. And then I can make sure that the action generator is generating dynamics that is consistent with the environment dynamics. So I can learn the low-level dynamics of the environment and make sure that the output is consistent. So the way to train this system is we have a lot of task-agnostic interaction. So the robot is randomly interacting with the objects. And we train the system simultaneously. One of the things to note here is that latent variables C and Z, the motion code and the effect code, are not supervised. Because they are not supervised, this model is basically doing variational inference for these hidden latent variables. So now, given a trained model, the way it works is you get an environment scene. The environment is observed as a depth image. The depth image is pre-processed as a graph network. Then the planner uses a scene graph of the object scene as input. The planner outputs a set of actions. In this case, the action is the position where the robot should go to, and then do delta poses around that position. I only gave the example of one task, which was crossing. So move the goal to a target goal across some constraint tiles. But there can be similar constraint tasks. Maybe we have to move the goal to a particular goal position with other objects in the field. And maybe a clearing task where I have to move all of the objects outside the blue tiles. One of the things to note here is, despite the tasks being different, we only have one data set and one model that was trained on task agnostic data. So what we see here is we can train the model. We can train the model and have both dense and sparse rewards. And what we are seeing here is, in case of dense reward case, so dense reward is basically providing a particular kind of reward structure that will help the policy solve the problem faster. We see an improvement in performance as we go from conventional MPC model predictive control to having learning-based MPC to having Gavin. And when we have sparse reward, where other methods perform slightly worse, the performance gap is larger. The interesting thing here is, because we are using, again, depth maps as input, we can go from sim to real without any fine-tuning. And what we see is the performance in the real robot is basically very similar. The big picture takeaway here is particular kind of structure or inductive bias in the model itself. In this case, the inductive bias was hierarchical dynamics model, or basically a hierarchical latent variable model in the dynamics, allows us to get better performance with sparse rewards. So in terms of qualitative results, we can see that in this case, the task is to put this box of Jello across the table. So the robot learns to move other boxes or bags of chip outside the path, and then it can push the box of Jello across the table. In this case, it's the bag of chips, and in this case, the best solution is to actually go around the obstacles. But in another case, maybe it's better to open a path and then push the object to the goal. So again, in this case, the two cases that we discovered or talked about are, in both hammering and pushing, what we are observing is that providing some sort of self-supervision. In both of these cases, the data was self-supervised, and structured latent variable models leads to both good representations, and they enable us to generalize to interesting problems at test time or plan time. In both of these cases, the data was generated through random self-supervised depth maps and random interactions. And in both of these cases, we used structured latent variable models, which enabled us to do multi-level reasoning. In the case of hammering, we were reasoning over what grasps to pick, and then how to optimize a policy conditional both on the state and the grasp. And in the pushing example, we had a dynamics model that was hierarchical. So before we move on, I would like to ask, do we have any further questions?
Okay, I cannot say any question, but any new question at least I can say. But there was a question, for the previous part of the presentation. Matthew actually asked. I'm not sure if it's still, it is her question. But let me just, yeah.
So just one thing I do. Yeah, go ahead.
Yeah, sure. Go ahead, please. Yeah, actually, she just asked that, can you explain how to choose the best teacher again? And aren't we aware of the knowledge of the teachers when we say that the agents would choose RL when the teacher's knowledge are not maybe sufficient to go?
Oh, okay. So for that problem, we are not looking for optimal teachers. Any amount of information is good. So the whole point of the setup is that it's not about optimal teachers. Any information is better than no information. That's one. The high-level critic is actually picking to use the teachers based on their value. So if it turns out that the policy you are training has superseded the teacher, the high-level policy will stop using the teachers.
Okay, nice. And you just mentioned about high level planner and low level planner. Is there any difference between high level planner and the global planner terminology? And for
Uh,
the low level one is the local one. Yeah.
yeah, I think you could use the global and local instead of high level and low level.
Okay, nice. Yeah, I think there's no other questions, so please
Okay,
go ahead. Yeah.
so let's continue.
Yeah.
Uh,
Nice.
so far we talked about these sort of like individual skills and maybe even like a couple of sort of multi-step skills like hammering and cutting. But a lot of the times, what we need to really do, maybe laundry or I don't know, cleaning up a garbage pile, the task is actually much more structured and requires pre-structured reasoning. So you can think about the laundry requires you to open the machine, pick up the objects, uh, excuse me, pick up the objects, maybe put soap in the washer, put objects in the washer, and you keep doing this until the bin is empty, and then you close the lid. And this process may actually be much longer, may require much sort of structured plan that is much larger, much more multi-step than what you've seen so far. Now, doing this where you have complex task structure with reinforcement learning is obviously much harder because it would be very slow. Uh, at the same time, doing direct imitation learning may not even be possible because you still require task segmentation in the data, which is non-trivial. So you have to, in the input data, provide me the example of, okay, this was loading the dishwasher. This was the part where you grab the object. This was the part where you put soap in, kind of thing. This is very hard. And then we don't want to learn only a fixed permutation of primitives. We want to be able to generally use the primitives in a very broad sense. What we really want to be able to do is what I would call meta imitation learning, where you get examples of a few tasks in this setup, but at test time, you are given, let's say, one example in this domain, and you are able to come up with a policy that will achieve this task. So let's think of what this means. So let's say a very simple domain, a task domain is basically, let's say, block world. A single task can be thought of as any particular configuration of these blocks. So there is instructional demos to complete certain distribution of tasks. But remember, the number of tasks that you can achieve in this domain is actually exponential, combinatorial. So the setup is we do multiple tasks in the same domain during train time. And at test time, you're given a single video of a new task, maybe a new configuration that you have never seen before. And you have to achieve this task at test time, and you have to come up with a policy to achieve this. Is it clear to everyone? If Moshtaba doesn't sort of intervene, then I believe it is. uh, so now doing something like this idea of one-shot imitation learning from videos has got a lot of attention in recent times, of course. But in almost all of those cases, the input demonstration, the video, is modeled as a flat sequence, and then policy is built on top. What we want to do, as Mushtaba was also referring, is to use this idea of compositional hierarchy. In this case, we use the model to represent the input data as hierarchy, and also the model itself as a hierarchy. And we'll talk about what sort of advantages using a compositional hierarchy provides us. So let's think about how a task like this in a very simple environment, like a block world, is done. Maybe the task is to put blue block on the red block. So to do this, you can maybe write a simple program that would do this task. So you have to go to the block and then grab and pick in place. But in this case, one of the things that happens is if you have to do a slightly different task, you have to write this program again. So we took advantage of this idea to create a meta-learning model where instead of writing programs, we basically said that let's have the model predict the programs themselves. So we instead pose the problem of hierarchical policy learning as a program induction problem. So in this case, you are given a demonstration video, a current state, and the output is actually what program to pick or what should be the next program. The training supervision here is for any given task, there is a demonstration and a hierarchical program trace of that demonstration. Now, to train this model, you would do something like a classification problem where every predicted program is compared with the ground truth program, which is available to you in simulation because the output of, let's say, a motion plan. Now, what does this look like? This looks something like this, that the model, given an input video sequence, outputs a program structure. This may look very complicated, but think about a very simple use case. Maybe you start with block stacking. Block stacking, in turn, becomes pick and place, which in turn calls a pick program. The pick program calls move to, and move to is an API level command that is passed on to the robot. Remember, we are calling move to. Move to is not learned, but what is learned is the parameter that is passed to this function, which is block E. So program is learning what high level programs to call in what order, and then what API level command to call with what functional arguments. Once move to is finished, the call pointer goes back to pick, moves forward to grasp part of the task. Once the grasping is complete, pick is complete, the call pointer goes back up to pick in place. Pick in place moves forward to the place part of the task. And now it is moving to the next block where the object needs to be placed. And then once this is complete, it places the object there. And this completes the pick place, which goes back to pick in place and the block stacking. Now the block stacking moves forward and the task can go on, so and so forth. Notice this was just one pick in place, but the tasks that we trained these models for required maybe even like tens of pick and place operation in some order. The interesting thing here is that the system is learning how to use a robot API. So this is essentially doing program induction. So at test time, what this looks like is you are given one particular demonstration. In this case, the demonstration is provided through VR, and carefully observe the configuration of the blocks. This enables the robot to initialize a policy that will achieve the same task. So if you can see, it's red, blue, yellow, green, and then the robot is basically operating the same task. But it's important to note, it was not just a parser. It was not that I parsed the demo into a sequence of actions and just did that. The system is actually a closed loop policy. So if it turns out that there is a failure or an adversarial agent because of which maybe part of the task that was already complete goes back, then the system knows that it needs to go back and fix what was wrong, rather than continuing on to just executing a past sequence of actions. So this idea of closed loop feedback policy exists. It's not just a parser of the demonstration. Now, to compare this quantitatively, we see that as the number of training tasks grow, a flat policy was basically a simple RL policy based on these images on test conditions does not actually perform very well, even though they may perform well on training tasks. So this was the example that I was mentioning earlier, that the train and test distribution in RL, if it is different, then the RL policy never generalizes. But this idea of posing the problem of hierarchical policy learning as a program induction generalizes very well. And in fact, with sufficient data, what we see is a very good sort of performance in terms of success rate. The interesting thing is we can always train it with vision input directly as well, not just state input. So vision input would basically be this idea of generic end-to-end model. And what we see is an end-to-end model gets a 60% success rate trained jointly. So the big picture, one point takeaway is that we get much better generalization than flat policy, and it provides us a mechanism to train a hierarchical policy with purely with vision. Now, of course, as in case of any sort of realistic setup, there are failures. The system can fail if the low-level API is not returning the right commands, or maybe there are collisions constraints that were not checked for by the high-level policy. So in this case, what we see is we went back to the drawing board to understand what sort of problem can we solve to improve performance here. So one thing that we noted is, in this case, we provided a particular kind of inductive bias to the input and output. So the output is a particular kind of program structure, but the model itself is a black box, end-to-end LSTM model. So the next set of problems we are thinking, maybe we can open the black box per se and put a particular kind of compositional prior. So make a model a particular kind of inductive bias itself that will help the system solve the task better. That bias is actually what we call the next task graph. So instead of producing a simple black box regression or a classification problem of what program to call next, now we basically think of having a parser of the demonstrator and use this parser to do what you would call a task graph generator. So a task graph generation is basically, let's say, I parse a sequence of actions from the demonstration, and then I also, based on my knowledge of the domain, I will also predict other actions that will achieve the same state. I will sequence them into a graph so that I can find paths from a given state to another state. This is called a neural task graph. So I'm doing graph completion. I'm thinking about other actions that were not even in the demonstration just because I know the domain. How do I know the domain? Because I've seen many examples of going from one state to another state, even though this particular state, start and end state, was not seen before. And then, given a task graph, I need a mechanism to execute this thing in a closed loop fashion as early. So now the interesting thing, or the most interesting argument here is, in these kind of compositional domains, we can have very many states, nodes, and a few actions. But the number of nodes is combinatorial. So learning a graph in terms of nodes can actually be very tricky because we do not have the memory to store as many nodes. So what we do is we learn this in a conjugate space where the number of actions becomes nodes. The edges are now preconditions and postconditions of actions. So things that need to be true for an action to actually happen, and particular states where the object will be after an action is completed. This is a finite state space or a finite representation model, which enables us to actually use a fixed memory representation for these task graphs. Now, what does an execution of a task graph look like? You get some sort of observation. The observation is passed to node localizer, which is basically saying what action just happened. Given the action, it predicts an edge classifier predicts what edge are you on, which is basically saying that what is the next state, and given the edge, you are picking the next action. Okay. So now, in this case, one thing to note is that the data that you need to train such a model is actually simpler. I have the demonstration and I have action sequence. In the neural task programming work, we were using full hierarchical supervision, which is much more structured. Action sequences are easier to obtain. So if we look at the results for the same set of tasks that we did earlier, but now we are going to evaluate it against NTP to NTG, what we see is with full state information, the performance gain is smaller, but with end-to-end model using vision, we see a 30% gain, a one-third basically gain in this system. The big picture takeaway of this argument is, with better compositional prior in the model and the correct inductive bias for the input and output, we can get better generalization in a harder task, which is using vision, and we can get better generalization even with weaker supervision. So in this case, we do not have the hierarchical supervision. So of course, the same set of this idea of NTP and NTG can be very general. It's not just block world. You can do object sorting from bins. You can do cleanup of dinner tables, or you can even do sequential search and prediction problems in navigation environments with these kind of setups. But the big picture takeaway really here is that compositional priors with modular structure enable generalizable learning in hierarchical domains. And in this case, the compositional priors were the program priors, both in the input-output structure and also in the model itself. So moving forward, we actually went back to study how can we sort of like continue this line of work to improve sample efficiency. In this case, what we observed is that we get good performance with weak supervision, but the number of training tasks required is of the order of thousands. And for every task, I need 100 demos, which means that I need 100,000 demos for this to work. And this can only happen in simulation. But what will happen in a realistic setting is we might not have such data. So what if we need to get similar performance, but maybe in the 50 training task regime rather than 1,000 task regime? So the question we were asking is, can we trade off demo data with problem structure specification? So right now we were using this idea of neural task graphs, which had low data efficiency, as I talked about. Now what if we can put more domain knowledge in the model itself? Now, if we have domain knowledge, this problem will become more like a symbolic planner. So what does a symbolic planner do? Symbolic planner does something like this. There is a state. The state is specified in a set of symbols, which are discrete sort of classifiers. A planner basically takes this state and picks the next action such that a goal will be achieved after a sequence of actions. This requires one that is called symbol grounding, which is basically taking the input in continuous input, let's say images, converting them into symbols, and then a planning model. To have a planning model, I need to understand what actions are valid, what states are valid, and what is the implicit dynamics model of the environment. So what does symbol grounding look like? Symbol grounding looks like image to some sort of symbolic state. So in this case, you can think of both blocks A and B are on table, so they are clear. In the next state, A is on B and A itself is clear. Symbol grounding network basically converts this into a classification problem to predict which of these states or state predicates are true. And a model that is doing symbol grounding may itself have structure. Maybe it is an object-oriented model that is predicting these things on the fly. Now, the interesting thing is that because this is a classifier model, machine learning-based classifier model, not all predictions will be perfect. Sometimes it may predict things that are not actually valid. So it may predict that object is both clear and object is on A and B. Notice that on A and B and clear B together cannot be true because they are invalid. But the system does not know about such sort of invalid states. If I have these invalid states and I put this into a symbolic planner, this will result in a planning failure. So now what do I need to do to fix this problem? One way to think about this problem is, instead of having symbols as explicit output of a classifier, we want to represent probability over the whole domain or possibility of symbols. So in this case, we can have a classifier that is going to represent the state as a probability distribution over possible states. But then I cannot use a traditional symbolic planner because it requires discrete states. That is where we will use a continuous relaxation of a symbolic plan. So what does this mean now? My states become distributions, and I replace the symbolic planner with a continuous plan. So what does this look like? In this setup, what we have is, we start with state representation. The state representation picks what actions are applicable at this point of time. Then I have to apply those actions. And then finally, I'm basically checking, is the state that I am currently in close to the goal or equal to the goal? If it is, then it is end. Otherwise, I repeat this loop. Now, in our case, the state representation is, of course, a set of probabilistic symbols instead of explicit hard classifiers. So then, to check if I have a particular state or not, I will basically represent this as the product of their probabilities. So the likelihood of you being in a particular state Now, given a particular action, I have to check which preconditions are active for me to be able to apply an action. So stack A on B requires me to check the precondition, is B clear? Am I holding A? Now, I have to do this in a continuous state. And what we do is basically, again, use this check in a probabilistic sense. So uh, highest likelihood preconditions will be the check. Now, what does it mean to apply actions? Because, well, we are in a continuous domain. So now, when we say stack B on A in a current state, can result in explicit stacking, but it can also result in incorrect stacks. So this can result in execution failure. So now, what this is basically doing in action application is we are pushing through the distribution after action application in two states, and we are basically comparing the states that are going to be valid before and after action application. So in this case, let's say holding A and clear B is a required precondition for stacking A on B. After that, only one of the states can actually result in success, while the others will result in failure of this action application. By the way, this is not the only action. You can have a list of actions that could be active in any given state. And goal satisfaction is basically direct comparison of probability distributions of two states. So now this sort of continuous relaxation also can be applied to the same set of problems that we were looking at in the same domain. Now we'll have a continuous planner which requires block domain definition specified. And remember, we are trading data for problem domain specification. The metric here is just final success rate. So if we compare performance here, NTG in very low task data regime is actually very low performance. We compare this performance with explicit symbolic planner, and then a continuous a planner with manual heuristics. So heuristics is the upper bound that you can get. And what we see is our learned continuous planner can actually be very close to the upper bound, even in very small data regimes. And what we see is this, in this case of null task graph formulations, in some cases, it can try to do the wrong configuration of the data, which the system does not know about because the system hasn't seen enough data. On the contrary, a symbolic planner will result in just invalid state and planning failure, while our continuous planner can reason through this sort of states in a sense of, in a probabilistic sense, achieving much more higher rate of success. And we can do this for other tasks such as object sorting, same sort of performance, where given an arbitrary a set of objects, they need to go into particular bins. The bin to object configuration can be changed on the fly. And similarly, we evaluate experiments on NTG, symbolic planner, and the manual heuristics. And we basically see that with very few training tasks, maybe 8 or 10, our continuous planner can actually achieve nearly 100% success. So now, so far, what we've talked about is how we can do one-shot imitation learning at different levels of regime. We started with 1,000 tasks and neural task programming. Then we added compositional structure in the system to enable us to do more efficient planning. And then finally, we thought about what happens in the low data regimes. So given the sort of, in the interest of time, what I'm going to talk about next is actually, just a second, is data. So far, what we talked about is this idea of control, then planning, then perception. But often what happens in these kind of cases, if you noticed, is as I'm solving incrementally more complicated tasks, my data that I have access to is decreasing. So if you remember, when I was solving control task upfront, maybe wiping the floor or something like that, we had millions of samples. Then we were doing hammering. Then I had maybe 500,000 samples. When I was doing structured tasks like blocks, then I had maybe 1,000 samples. But what happens is, if I want to do realistic tasks like procedural execution from videos, the data requirement is actually going to grow rather than shrink. But we have no mechanism to get such data. So the real question here is, how are we going to get such large structured, large sets of data with structured supervision? So what do I mean by structured supervision here? It's basically the structured supervision is the structure of the task, which has both perception and planning structure. People in robotics have used imitation learning, and it has actually performed very well. It has outperformed pure RL. In recent years, we have seen a lot of interesting results using imitation. But if we look at the data sets that are being used for these tasks, it's actually very small, surprisingly small. It's about minutes of data. But the reason why these data sets are usually small is because collecting data on real robots is very hard. You almost always are collecting data by holding robot hands, and this can be very slow. Just to compare what data sets look like, these are the sizes of data sets that are very popular in robotics these days. And if you compare this with our colleagues in computer vision and NLP, we are orders of magnitude off. So now the question we are asking is, how do we scale this data set? People in vision and NLP use large-scale supervision through maybe Amazon Mechanical Turk or something. But in robotics, we need to demonstrate, not label. So such simple expansion is not possible. The reason is usually providing this demonstration requires teleoperation, but teleoperation is not easy to do because on simple devices that everybody has, data is usually degenerate. On special purpose devices where data is good, but these devices are expensive and maybe an average crowd worker would not have them. So what we created is basically a mechanism to put robotics to mechanical Turk, and we call this RoboTurk. What it needs is basically a very simple interface that you can download on your phone, maybe as an app, and you can control a robot in full degrees of freedom to achieve this task. All you need is basically a computer screen in a browser and a phone app to do this thing. And again, this works with not just simulation, but also real world robots as well. So this allows you to control not only simulated robots, but maybe even real robots to do interesting tasks that reinforcement learning cannot do right now, to collect data on these tasks. And again, you can do this at scale from a variety of different locations, and the workers can be in whatever place they want, maybe home, coffee shop, library, or wherever they are. They don't even have to be in the same city for that matter. And now what we did was we used this framework to collect lots of data, hundreds of hours of data in about 1 week of usage. Just to give you a sense how this compares, we get 10x larger data sets in about 1/10 of the time that other data sets were collected in. So just to see how the data may itself be useful, we look at two simple tasks on which we collected data, and we see that by injecting demonstrations using a sparse reward setup, even with a lot of compute in RL, we get no performance. But as we can inject more data in the system, we can get more performance in terms of success. Not only this, we can use the data set to learn image-based features. So in this case, this is unsupervised representation of the video that is completely learned from data collected. In this case, what you are seeing is a representation of key points that are sufficient to represent this video and reconstruct this video. Using this representation, we can train a policy using batch RL or offline RL. Offline means that I'm only learning through data that I have. I don't have the ability to actually evaluate my policy on the real environment, as is possible in regular RL. And what we see is this already gets us a performance of 50% on these hard pick and place tasks without ever interacting. So Iris is our paper, and it's much, much better than something like behavior cloning, which would be direct supervised learning of states to actions. So the big picture idea here is that structured supervision for robotics is very important for us to scale robotics to more complex tasks. And this structured supervision is available to us through scalable crowdsourcing that can empower us to do robotics or robot learning in more complex tasks and unlock this treasure trove of information that people in vision and language have used, but robotics has not been able to access. So with that, I know I'm out of time. I would like to sort of remind that I talked about different algorithms at different levels of abstractions. We started with control. We talked about how pushing and how pushing algorithms or how reinforcement learning with teachers can be made more efficient. Then we talked about how putting some sort of hierarchical latent variable structure in the model enables us to do reasoning to use tools, reasoning to use pushing for multi-step planning. Then we talked about one-shot imitation, where we talked about how we can use program induction as a mechanism to do efficient policy learning directly from videos. And then finally, we talked about how we can leverage data in these structured tasks. But if you remember one thing from today's talk, let it be just this. Learning with structured inductive biases and priors at different levels of abstraction in robotics, not just robotics, but reinforcement learning and decision making in general, enables a much more efficient and generalizable algorithm design. Efficient in terms of sample efficiency and generalizable to multiple problems or variations of the problem. And finding the right structure is going to be the next stage of research questions in this space. Because we are out of time, I would sort of rest my case here. I would like to thank a number of people who were involved in this work, a number of robots who were involved in the making of these videos over the years. And I'd like to leave it here, where I have my contact information, my current lab, and happy to answer questions at this point. Thank you very much.
First of all, I would really like to thank you, Animesh, for your very deep, I can say, presentation. Actually, a very cool one.
Thank you.
Yeah. So I think that there is a couple of questions. At least I have some. If in the meanwhile that they are thinking. Actually, Hadi in the middle of the presentation just asked one question. But I cannot recall for the which part of the presentation. But he just
it's fine. Yeah, go ahead.
Yeah. Could you explain the evaluation metrics? Why you have been shown that with a number of training?
Okay. So I think this is for neural task programming and neural task graphs line of work, where the number of training tasks and the number of test tasks. So just to remind you, the setup was meta reinforcement learning, where we have a domain where we can construct different tasks by different final configuration of blocks. Each configuration of block can be thought of as one task. So when I say number of training tasks is basically picking that configuration of block. So from an arbitrary start state, you need to get to that configuration of blocks. Number of training tasks is number of those tasks. And then the training data set consists of, let's say, when I say 1,000 training tasks, it means that 1,000 configurations. For each configuration, I get 100 demonstrations. So I get 100,000 demonstrations to train the model. Is that clear?
Yeah, I think so. Actually related to meta reinforcement learning, we know that meta reinforcement learning is really promising. But actually, I have a question for, let's say that we have a very complex task, and then we want to somehow divide this complex task to some subtask. I think that still we have some sort of problem that how we can in a generalized way, in a general way, to just somehow find this division. It's a very good one maybe. So let's say that for example for Atari games, you know that for each game there are different kind of object, even there are different kind of tasks that you have to achieve. So if you want to solve all the games, all the Atari games, and in let's say that for the current definition of the generalization in the Atari settings of the RL, then this is not going to be achievable, by this kind of thing, because it's not absolutely possible to just use supervised information from the human to just label all the tasks in each game, and that's going to be a problem. So what do you think about that?
So we are not labeling all the tasks in the game, right? Remember, we can combine different kinds of algorithms. You can combine the algorithm that we provided by providing partial exploits. So maybe you cannot. So first of all, human supervision is not necessary. First of all, but human supervision speeds up learning by multiple orders of magnitude, and it has a lot of value. That's one. Many tasks are too hard to learn purely with simulation, perhaps because we do not have simulators, right? So Atari Games is a special case where compute is free. I can throw a lot of compute without worrying about any sort of complication there. So I can solve this task purely from scratch. But in many robotics tasks, we do not have that liberty. Compute is not free in the sense, first of all, simulators don't even exist. You have to do this in real robots. And whenever simulators do exist, they are much more expensive than simple Atari games. That's one sort of argument. The other is, I did not talk about the solution to this problem. We have meta learning algorithms that can achieve these tasks. Just yeah, that achieve these tasks in a manner that would discover the hierarchy and do this automatically, purely in a reinforcement learning sense, without having human demonstrations. This paper was published a few weeks ago at a conference called UAI, and this is, I believe, the state of the art in meta reinforcement learning. The algorithm is called Ocean, and yeah, it's also on my website, by the way.
Okay, perfect. That's great. So, as another question, for the probabilistic models that you just mentioned, and you just use that, and I think that you showed that they are much more robust, to the invalid action and all the other things. But there is still one question for me. If you let's say that sometimes if you don't do any action, for example the no operation settings, then maybe it is much more better for the RL algorithm to maybe choose the most probable action. Let's say that the most probable action is just the probability for the most probable action is not really high, so you're not really confident to choose even the strongest action that you have. But maybe sometimes act do not acting is better than acting. I don't know, is that the case?
So this is not just going to pick a most probable action. Remember, this is using a planner. So there is no human data to sort of bias the action. You are going to use the action such that the next state is actually closer to the goal.
I see. Yeah, perfect. Actually we have a question from Ali Reza. He just asked that, what do you think about the role of GAN in simulation of RL projects?
Oh, yes, a lot. So, of course, I didn't talk about a lot of the vision projects that we are doing. You can use GANs for doing a lot of interesting things. For example, you can transfer styles. So let's say I collect demonstration in one style, and then I want to transfer the demonstration to a different style, maybe human to robot or object to object, where my object was green colored and your object was red colored, and so on and so forth. That's one. The GAN itself could be used not just for perception, but maybe even for the policy itself. So, for example, a lot of success has been achieved through this line of algorithms called GALE, which is called generative adversarial imitation learning, where you set up the imitation learning problem as a GAN, and the imitation is basically the data distribution is trajectories that are provided to you as demonstrations. And what is the GAN doing? The GAN is basically saying that if my policy generates data, can I differentiate between the policy generated data and the demonstration data? So you're basically saying that if my policy does the task, can my discriminator tell the difference between this trajectory and the trajectory in the real data? And if I can make sure that my policy is generating data that is indistinguishable from trajectories of the real data, then I must be doing the right thing. So it can be trained as a GAN objective, but in an RL sense, and that line of work has gotten both a lot of attention and deservedly so.
Okay, nice, perfect. Thank you for your answer. As a last question for me, I was wondering that, as someone that absolutely is experienced, in this kind of research, what kind of framework are you using now, and is that really open source? Is that accessible in an open source manner, or do you really suggest any kind of RL framework that is useful for this kind of research? And if there is any kind of advantages or disadvantages that you are aware of, many similar open source frameworks that are available for reinforcement learning. I really appreciate that. Yeah, perfect.
So there are multiple open source reinforcement learning frameworks depending on what use case you are having. Depending on, let's say, are you looking at a discrete state action problem, a continuous state action problem? What sort of dynamics will the problem have? Is it a navigation problem or a manipulation problem or a different problem altogether? And then the algorithms can be model free, model based, off policy, on policy. Depending on that choice, the choice of algorithm matters. Now, not all implementations of all algorithms that are available on GitHub will perform the same. But using, let's say, standard implementations, either by something like RLlib, which is built for distributed sort of implementations, or some implementations by, I think, Google. Google has something like TF agents. Then OpenAI has stable baselines, and there are versions of stable baselines. So there are a number of these sort of like open source implementations of these algorithms. But one thing that we found out in our experience is not all versions of algorithms work similarly for all sorts of problems. Often these algorithms are evaluated on simple Mujoko tasks, the gym environments. They are not very similar to, for example, robot manipulation environments. So performance can vary depending on what your task is.
Okay, perfect. Majid actually asked that why couldn't we use videos related to this kind of action to learn robots to learn? Here I'm not sure if I just will have we any paper about extraction action object from videos? That's the question actually.
So how to extract objects from videos? Is that the question?
Let me read that again. I'm not really sure that I just understood the question well. So the question is that why couldn't we use videos related to this kind of action to learn robots to learn? Have we any paper about extraction action object from videos? There is some sort of misunderstanding for me. So maybe you can clarify.
Yeah, I think if the person can clarify, that would be very good. If I understand the question correctly, do we have any papers that do some sort of object extraction in a learning to learn sense? I do not personally have that paper, but a few of my friends have worked on that problem where some of the perception problems are being looked at from the lens of reinforcement learning, in the sense that if I have multiple tasks, can I learn the representations that are better for perception? So, for example, one of the projects that we're working on actively is what sort of 3D representation of objects are useful for decision making downstream. And if I basically do this in a learning to learn sense, then I can come up with common representations that are useful in a multiplicity of tasks downstream. That's what I can say. Yeah. If there is a clarification on the question, feel free. Yeah.
Okay, perfect. Just to add to your comments, actually, if it is related to object extraction for reinforcement learning, I think that there is a paper in Norif's 2018 It is the paper called Model. It's, they are somehow trying to extract the moving objects by an unsupervised object flow segmentation, let's say, to just automatically extract the object in the picture, and then they are going to they just shows that the algorithm is much more efficient in the sample complexity. So
Absolutely. I
maybe,
will.
yeah, maybe that
I
can
think
be.
I know the paper, but I will look into this much more. Thank you very much for
Okay,
the
nice.
point
Yeah,
pointer.
sure. I'm not sure if there's any other question, but if you like to add any sort of comment or whatever you like, yeah, please feel free to do that anyway.
No, I think according to me, this is one of the most sort of exciting areas of AI. This is this enables a lot of this requires progress in multiple fields. At the same time, it requires me to be very close to making things work in a physical sense. So the problems in this space are sort of open world. There's so much to do. This is so exciting. At the same time, this is what you would call AI complete problems, where you actually have a real robot that needs to have visual understanding, that needs to have sample efficient reinforcement learning and decision making. It needs to have generative models of dynamics in its head, and so on and so forth. So according to me, uh, this is the area to be working in. And I invite some of you, hopefully you'll pursue careers, whether academic or industrial careers in this space. And yeah, all I can say is hit me up if you have questions. You have my contact information. And yeah, all the best to you guys
Yeah.
going forward in this career.
Yeah, thank you so much for your time. I just want to, let the participant again know that if they have any question or inquiry, they can absolutely refer to the website of this conference, and they can contact the organizer if you do have any kind of problem. Because this is the last session, I think that we are going to, I hope that you just had a, let's say, good conference for all the sessions, and hopefully see you next year. Thank you so much.
Absolutely.
Yeah. Goodbye.
Absolutely.
I can
Thank you
say.
so much.
Have a good day.